Hey, what's up, everyone? Welcome back to Kinetics. Today we're going to be talking about collision theory. So collision theory tells us that the rate of a reaction is dependent on the number or force of collisions. So what does that mean? Collision theory has three little postulates, and they lay the requisites for when a reaction can occur. So the first one is that reacting particles must collide. And to go through the postulates of collision theory, imagine this analogy where you have a pen without a cap reacting with a pen cap to form a capped pen. All right, so if you have these reacting particles, if you have the pen and the pen cap never colliding, then you are never going to create the capped pen. In this case, the pen and the capped pen are just going to miss each other and no reaction ever occurs. So you never get your capped pen. The second postulate is that reacting particles must collide with proper orientation. So take the same reaction where a pen without a cap and a cap are reacting to form the capped pen. In this case, you have the pen cap and the pen colliding, but you'll notice that the pen is oriented the wrong way. And when this happens, when the particles collide, you get a capped pen, but it's capped the wrong way. It's not the orientation that you want. So you never end up getting the product that you want. So these reacting particles must collide with proper orientation. If in this case, this pen over here was flipped, if the tip was on this side and the end was on the other side or whatever, then you would have the right product. The third one is that reacting particles must collide with sufficient energy. And this one's a bit harder to imagine, but if you go to cap a pen and you don't use the right amount of pressure, you don't hear that click, and then when you go to flip it upside down, the pen cap falls right off. So you can think of it like that. In the terms of molecules, when molecules collide, what's happening is that if they have enough energy, they break the bonds within each other and they reorganize the bonds to form the products. So you can imagine if you don't have the right amount of energy, the bonds never get broken, so new bonds never get formed, and you don't have any products being formed. So reacting particles need to collide with the right amount of energy. And we'll talk more about what that right amount of energy is in a little bit. All right, so this was collision theory. The rate of a reaction is dependent on the number or force of collisions. These were the three postulates. Reacting particles must collide, reacting particles must collide with proper orientation, and reacting particles must collide with sufficient energy. And this brings us to the major big idea of collision theory. And it's that as you increase the number of collisions, the rate of your reaction goes up. So you can think about this in terms of temperature. As you increase the temperature, your reacting particles move much faster, so you have more collisions happening, which means that you have a likelihood of more of those collisions having the right orientation and energy. Therefore, your reaction rate increases. You have more collisions, you have a higher reaction rate. You can also think of it in the number of particles. So if you just add more particles into the chamber, when they move around and they collide, there are more molecules to collide with. So more collisions happen, and therefore the rate of reaction also increases. You can also think of it in terms of reactant surface area. So if you've ever been in a lab, you know that they crush up some of the reactants, and that's to increase the surface area. So there's more places for reacting particles to collide with. You increase the number of collisions, and therefore you increase the rate of your reaction. And that is the big fundamental idea of collision theory. As you increase the number of collisions, your reaction rate goes up. All right, I want to talk about two of the postulates of collision theory in a bit more depth. And the first one I want to talk about is number 3. Reacting particles must collide with sufficient energy. So what is sufficient energy, and how do we know what that is? In order to find that, you need to look at the reaction coordinate diagram for a reaction. And in a reaction coordinate diagram, on the y-axis, you have potential energy. So that represents the energy of the system at some given time. And the reaction coordinate represents the progression of the reaction. So all the way on the left would be when you have all reactants. And then all the way at the end, when your reaction coordinates all the way at the end, meaning your reaction is completed, you have all products. And so in this case, the potential energy of our reactants is lower than the potential energy of our products. This means that it was an endothermic reaction. If your products was below your reactants, that would be an exothermic reaction. But all reaction coordinate diagrams are going to have your reactants and your products. The products might be above or below, depending on whether or not it's endothermic or exothermic, but you have them. Now, the interesting thing is what happens in between the reactants and the products when you look at how the potential energy changes over time. And all reaction coordinate diagrams are going to have a similar shape for this like area between the reactants and the products. You have the energy going all the way up, the potential energy goes all the way up until you reach this, maximum. And that maximum is what we call the activated complex or the transition state. And then from there, the energy goes down until it goes back to products. Now that activated complex or the transition state, if you look at the energy of that complex and you subtract it from the energy of your reactants, you get your activation energy. It's signified by EA. And in this case, since your activated complex is at 25 kilojoules per mole and your reactants is at 5 kilojoules per mole, your EA would be 25 kilojoules per mole minus 5 kilojoules per mole. So 20 kilojoules per mole. In this case, your activation energy is 20 kilojoules per mole. So this number represents the threshold that reacting particles must collide with. So if your reacting particles collide with more than 20 kilojoules of energy, they can actually form products. But if they have less than that amount of energy, they can't get over this potential energy maximum, and therefore they can never form your products. Think about like riding a bicycle up this hill. There needs to be a sufficient amount of energy. There needs to be a threshold of energy that you must output in order to get past the hill. If you don't have that, you fall back down and you just can't form your products. So the reacting particles must collide with sufficient energy. It's what we call your EA, your activation energy. And your activation energy is helpful in a bunch of equations and other kinetic stuff. And the reason for that is because your activation energy is independent of temperature. So for a reaction, your EA is always the same. That's why it represents like a constant that we can use for different equations to vary, different other conditions. The next thing I want to talk about is number 1, which tells you that reacting particles must collide. And so you can have different types of reactions based on how many particles collide. You could have unimolecular, where it's just one particle colliding with, I guess it's kind of counterintuitive to think that one particle just collides with itself. But when one particle produces products, we call that a unimolecular reaction. When you have two, we call that bimolecular, so two particles colliding to form products. And then if you have 3 or more, you have termolecular reactions. Now, try to think about the frequency of termolecular reactions as compared to unimolecular or bimolecular reactions. And to think about it, imagine yourself in a room with 30 other people, and you're all blindfolded and you're just told to walk around. You can think of unimolecular reactions happening when you just collide with the wall. You can think of bimolecular when you collide with one other person, and then termolecular when you collide with 2 or more other people. You're going to run into the wall a lot. You're going to run into one other person a lot. You're going to have a lot of unimolecular and bimolecular reactions. But you're not going to have a lot of termolecular reactions because it's really unlikely for 3 or more people to collide at the exact same time with each other. And even in this analogy, you're a person in a room. So you have a decently significant volume. But you can think about gas particles in a container. Their volume is just so little that it barely makes sense for 3 or more particles to collide at the exact same time. And so termolecular reactions are many times more unlikely to happen than unimolecular or bimolecular reactions. And for that reason, whenever you see a normal chemical equation and you see on the reactant side you have like 4, 5, 6 particles colliding at the exact same time to form products, that's indicative that that reaction is not happening in just one step. You have a series of unimolecular, bimolecular, maybe 1 termolecular, maybe 3 particles colliding at the exact same time, but it's usually just going to be unimolecular and bimolecular, a bunch of small of those reactions that all add up to form a complete chemical equation. And so for a reaction, we say that the reaction has a reaction mechanism by which smaller elementary reactions help build up to the final chemical equation. And so reacting particles need to collide, and having 3 or more particles colliding at the exact same time is really unlikely, so we have reaction mechanisms, which we'll talk about more in the next video. One last note about collision theory is that technically collision theory only applies to gas phase reactions. This only works if you have gases, but technically collision theory applies a little to reactions happening in aqueous solutions, but just know that collision theory only technically applies to gas phase reactions. And that's all I have for collision theory. I hope this was helpful. I hope you were able to learn something, and I hope to see you later. Thank you.